Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says. For years now, we've been tracking the incredible progress of AI in software engineering. We've seen agents that can write code, fix bugs, and refine solutions for GitHub issues. But in AI-driven software engineering, there's been this fundamental bottleneck. You have to run the code to know if it works.
Exactly. The execute and fix loop, we call it. An AI writes a bit of code, compiles it, runs it in a secure sandbox, sees if it passes tests or throws errors, and then tries to fix it. It's like the AI is constantly poking at the system, waiting for a reaction to learn. It's effective, but it's also incredibly slow and resource-intensive.
And that's why this new paper from Meta, Agentic Code Reasoning by Ugare and Chandra, caught my eye. They're proposing something genuinely radical, an AI that can reason about code, spot flaws, and even verify patches without ever running the code. And the accuracy they're claiming? 93% on real-world agent-generated patches. That's a game changer if it holds up.
It's a huge leap. It fundamentally challenges the premise that execution is an unavoidable step in validating code, especially for AI agents. They're essentially teaching an AI to dry run code in its head, much like a seasoned human engineer would.
So let's unpack this execute and fix loop first, because to understand the breakthrough, we need to understand the problem they're trying to solve. When we talk about these autonomous software engineering agents, how do they typically operate? Are they just writing code and hitting save?
Not at all. Imagine you give an AI agent a GitHub issue. Say, fix this bug in the login flow. The agent doesn't just churn out a patch and call it a day. It writes a patch, then it spins up an isolated environment, compiles the code, runs the test suite, and waits for the outcome. If it fails, which it often does on the first try, it reads the error logs, analyzes the traceback, and then tries to refine its solution. This is the core of that execute and fix loop.
And this sandbox environment you mentioned, that's crucial for security, right? You can't have an AI just running arbitrary code directly on your systems.
Absolutely. These sandboxes are vital. They're essentially secure, isolated virtual machines or Docker containers where the AI's generated code can run without compromising the host system. It's a necessary safety measure, but it introduces immense friction.
Friction in what sense? What are the biggest pain points with this approach?
There are three main areas. First, computational expense and latency. Spinning up a secure sandbox, resolving dependencies, compiling code, especially in complex languages like C++ or Rust, and then running a full test suite can take minutes for just one iteration. If an agent needs dozens of attempts to fix a tricky bug, that latency compounds quickly. It becomes economically and temporally unviable for real-time assistance.
So it's not just slow, it's expensive to run all that infrastructure for every single attempt.
Precisely. Which brings us to the second point, security and infrastructure overhead. Maintaining robust security boundaries to prevent sandbox escapes or malicious network requests from untrusted AI-generated code is a massive operational burden for any enterprise. It's a constant battle.
And the third one, the paper highlights, is perhaps the most critical bottleneck for the future of AI itself.
That's the reinforcement learning, or RL, blockade. This is where the bleeding edge of AI development is headed, similar to how RLHF is used for conversational models. In RL, an agent performs an action and needs an immediate reward signal to learn if that action was good or bad. If calculating that reward means spinning up a sandbox and running a test suite, your training pipeline slows to a crawl. To train the next generation of truly capable coding models, AI labs desperately need execution-free reward signals. It's like trying to train a race car driver, but every time they make a mistake, you have to rebuild the entire car from scratch before they can try again.
So the goal of agentic code reasoning is essentially to give the AI the ability to do that dry run in its head, like a human senior engineer reviewing a pull request. A human doesn't necessarily compile and run every line of code to spot a logical flaw or a race condition.
Exactly. A human engineer traces the state of variables, follows function calls, and performs a mental simulation. The Meta researchers hypothesized that if an LLM is guided correctly, it could perform the same execution-free dry run with high reliability. That's the premise: navigating files, tracing dependencies, gathering context, and performing deep semantic analysis without executing the code.
Which leads us to the core of their methodology. If LLMs are so powerful, why couldn't they already do this dry run effectively? What was holding them back?
The answer lies in the limitations of standard chain of thought, or COT, prompting. If you ask a model to evaluate a code patch today with a simple, let's think step by step, LLMs at their core are probabilistic pattern matchers. They're designed to predict the next most likely token. When left to their own devices in an unstructured COT format, they often guess rather than truly prove.
So they might make a claim about code behavior, but without really having the explicit justification for it. They just sound right?
Precisely. As a DevOps.com analysis of this paper pointed out, standard COT allows agents to make claims without explicit justification. An agent might conclude two patches are equivalent because they look similar, or it might assume a helper function behaves a certain way without actually looking at its definition. It pattern matches what a code review looks like, generating authoritative-sounding text while potentially skipping crucial edge cases or even hallucinating logical leaps. It's like a student who can write a convincing essay about a math problem but can't actually show the steps to solve it or tell you why those steps work.
That's a perfect analogy. So what did Ugare and Chandra do to combat this semi-formal reasoning methodology they developed?
It's not a new model architecture, which is important to emphasize. It's a highly structured prompting methodology. Think of it as a logical constraint designed to force the LLM to be rigorous. The core concept is what they call a reasoning certificate.
A reasoning certificate? What does that entail? How does it force the AI to be more rigorous?
It forces the agent to adhere to a strict analytical template before it's allowed to generate a final answer. If the agent can't provide concrete evidence for a step, the logical chain breaks. This prevents unwarranted assertions. In practice, it requires the agent to do three things. First, construct explicit premises. Before making any claim, it must state what it expects to find and document its observations with exact line numbers, citing a specific file line for every claim.
So it's like a lawyer presenting a case, where every piece of evidence needs to be cited with page and line numbers.
Exactly. Second, it has to trace execution paths. The agent is forced to enumerate all relevant test and code paths. It must trace interprocedural calls, following a function call from one file into another rather than just assuming behavior. And third, it must derive formal conclusions. It can't just say, this looks good. It has to provide a formal conclusion, either demonstrating the explicit absence of behavioral differences between two patches or providing a concrete line-by-line counterexample where the logic fails.
That's incredibly granular. It sounds like it's trying to bring the rigor of formal verification into the more flexible world of LLMs. Is that the intent?
It is. This methodology sits strategically between two extremes. On one end, you have unstructured COT, fast, flexible, but unreliable and prone to hallucination. On the other, you have true formal verification, which translates code into mathematical languages like Lean or Coq. Formal verification is mathematically perfect, but incredibly brittle and practically impossible to use on messy, multi-language enterprise codebases. Semi-formal reasoning tries to bring that rigor without the brittleness, bridging the gap using natural language.
Okay, so the methodology sounds clever, but as you always say, the proof is in the pudding. Does it actually work? What did the empirical evidence show across the different tasks they tested?
The results are quite compelling. They tested it across 3 distinct software engineering tasks, and in each case, forcing the AI to show its work led to massive performance gains. Let's start with patch equivalence verification, which is arguably the most critical test for this kind of agentic code reasoning, determining if 2 different pieces of code achieve the exact same semantic result.
Right, crucial for refactoring or optimizations where you want to change the code structure without changing its behavior.
Exactly. On a dataset of challenging, curated patch pairs, standard unstructured reasoning achieved about 78% accuracy. But by applying the semi-formal reasoning template, accuracy jumped to 88%, a full 10 percentage point gain. But it gets even more striking. When they tested this methodology on real-world agent-generated patches using the state-of-the-art Opus 4.5 model, it achieved an impressive 93% verification accuracy.
Wait, 93% accuracy on real-world patches without running them? That's the number that really jumps out.
It is. To put that in perspective, single-shot prompting only achieved 86%, and traditional difflib-based similarity checks, which just compare the text, hovered at a mere 73%. So the structured reasoning isn't just a marginal improvement, it's a significant leap in reliability for this task.
That's incredibly impressive. But patch equivalence is one thing. What about contextual understanding or finding actual bugs? Did it help there too?
Yes, on both counts. To test contextual understanding, they used something called Rubber Duck Bench. This benchmark, developed by researchers at Bryn Mawr College and Google DeepMind, is derived from real-world GitHub pull request comments. It tests an AI's ability to answer complex, contextualized questions about a repository without hallucinating API behaviors. When Rubber Duck Bench was introduced, even top models like Grok 4 and Claude Opus 4 struggled, achieving only 67 to 69% accuracy and hallucinating in over half their unstructured responses.
So LLMs were basically making things up about how the code worked.
Frequently, yes. But by applying the semi-formal reasoning methodology, the meta-researchers pushed accuracy on Rubber Duck Bench to 87%. That's a massive 9 percentage point gain over the standard agentic reasoning baseline, proving that structured constraints drastically reduce hallucination and improve deep contextual understanding.
That's fantastic. Reducing hallucinations is a huge win for any LLM application. And then for fault localization, actually finding where the bugs are?
For that, they used the Defects4J benchmark, a classic dataset of real, reproducible bugs from open-source Java programs. Here, semi-formal reasoning improved top 5 accuracy for fault localization by 5 percentage points over standard reasoning. So whether it's verifying patches, answering questions about code, or finding bugs, the method consistently outperformed unstructured approaches. It proves the agent is better at finding the needle in the haystack when forced to trace variables methodically.
The implications of this research seem to extend far beyond just winning benchmarks, though. The paper suggests this could fundamentally change how we approach software development. What are those bigger ambitions?
One of the most significant ambitions is that semi-formal agentic reasoning could serve as a flexible, generalized alternative to classical static analysis tools.
Like SonarQube or Coverity, the tools that lint your code and look for security vulnerabilities?
Exactly. Traditional static analysis tools are foundational to modern DevOps, but they're rigid. They rely on abstract syntax trees and control flow graphs, and building them requires hard-coding specific logic and rules for every single programming language and framework. You can't easily run traditional formal verification on a modern web patch that simultaneously touches Python backend logic, Django middleware, HTML templates, and SQL database queries. The semantic context is too fractured for those tools.
So, instead of building a separate custom tool for Python, then Rust, then HTML, you could theoretically have one smart LLM-based system that understands all of them?
That's the vision. LLMs are naturally multimodal across text and code. The researchers note that instead of encoding analysis logic into specialized algorithms, developers could simply prompt LLM agents with task-specific reasoning templates that naturally generalize across languages and frameworks. An AI agent doesn't care if the file ends in .py, .rs, or .html. It reads the logic semantically. If semi-formal reasoning can make this process rigorous, it could absolutely disrupt the entire static analysis industry.
That's a huge potential impact. But then there's the Holy Grail application you mentioned earlier, the one that excites AI labs the most.
Yes, the execution-free RL reward signals. Remember how we discussed the Sandbox bottleneck choking reinforcement learning pipelines? If a reward model has to score a patch by executing it in a sandbox, the training loop becomes computationally exorbitant. By achieving 93% accuracy in patch equivalence verification without execution, Ugari and Chandra have demonstrated that LLMs are approaching the reliability needed to serve as these execution-free reward signals.
So, future coding models, like an Opus 5 or GPT-6, could be trained exponentially faster because they wouldn't have to constantly run code to get feedback. They could just get semantic feedback instantly.
Precisely. They could evaluate millions of synthetic patches purely through these semantic dry runs. This is a massive leap towards scalable, repository-level AI software engineering. It means faster iteration, more data, and ultimately more capable coding agents.
Okay, this all sounds incredibly promising, even revolutionary. But this is paper trail, and we always have to apply some rigorous journalistic skepticism. What are the major areas where we need to push back, or where the paper itself acknowledges limitations?
You're right to ask. There are three major areas. The first, and perhaps the elephant in the room, is data contamination. The benchmarks used to prove the efficacy of semi-formal reasoning, specifically SW Bench and Defects4J, are highly public. Defects4J, for instance, was published in 2014. It is a near certainty that the instances, bug reports, and exact human-written patches from these benchmarks exist in the massive pre-training corpora of models like Opus 4.5.
So the question isn't whether the model can reason, but whether it's truly reasoning or actually just retrieving a memorized solution with the help of the template.
Exactly. When the model traces a bug in a 2014 Java repository, is it doing deep interprocedural semantic analysis, or is it pattern matching a Stack Overflow thread it read during training? The authors themselves admit this contamination could inflate the absolute performance numbers, while the delta, the 10% improvement over standard COT, is likely genuine. The absolute 93% accuracy figure must be viewed with a skeptical eye.
That's a crucial distinction. What's the second area of pushback?
It's what I'd call the illusion of formality. The terminology semi-formal is brilliant marketing, but it risks lulling developers into a false sense of security. It's vital to clarify that this is not formal verification. Formal verification relies on deterministic mathematical proofs. If a lean or cock proof compiles, the code is mathematically guaranteed to adhere to its specification.
But semi-formal reasoning is still an LLM, generating text.
Right, it's still probabilistic text generation. The LLM is predicting the next most likely token. It's constrained by a template, and it's forced to cite line numbers, but it is fundamentally simulating logic, not computing it. A hallucination wrapped in the authoritative structured language of a formal proof is arguably more dangerous than a standard, obvious hallucination because it looks perfectly convincing to a human reviewer. This is a manifestation of the clever hands effect. The AI appears to be doing math, but it's actually just reading the cues of the template.
So it's a very convincing magic trick, but still a trick. And that leads directly to the third point, doesn't it? The real-world implications of that 7% margin of error.
Absolutely. The paper boasts a 93% accuracy rate on real-world agent-generated patches. In the context of creating a reward model for RL training, 93% is a triumph. Some noise is acceptable in an aggregate training run. However, in the context of replacing static analysis or automating code review in production, 93% is, frankly, terrifying.
Terrifying because that leaves a 7% margin of error.
Exactly. If an enterprise DevOps team integrates this execution-free sandbox into their CI/CD pipeline, 7 out of every 100 patches will be incorrectly verified. In mission-critical software, aviation systems, banking backends, healthcare databases, an AI confidently hallucinating a formal conclusion that a vulnerable patch is safe could introduce catastrophic security flaws. As cybersecurity analysts noted earlier this year, threat actors are already exploring ways to manipulate AI dependencies and agentic workflows. An automated reviewer with a 7% blind spot is a prime target for adversarial exploitation.
So while the speed and efficiency gains are incredible, we have to be incredibly careful about where and how this technology is actually deployed in critical systems.
Precisely. It's a powerful tool, but like any powerful tool, understanding its limitations is as important as celebrating its capabilities.
This has been a truly fascinating deep dive. So, to wrap things up, what do you think are the key takeaways our listeners should really carry with them from this research?
I'd say there are four main points. First, the traditional execute and fix loop is a major bottleneck for AI software engineering, particularly for training the next generation of models via reinforcement learning. Second, structured prompting, or semi-formal reasoning, dramatically improves LLM code analysis capabilities without needing to execute the code. Third, this has immense potential to accelerate AI training and could revolutionize the static analysis industry. And finally, and crucially, we must approach these results with skepticism, acknowledging potential data contamination, the probabilistic nature of LLM reasoning, and the very real risks of even a small margin of error in critical systems.
And as we look to the future, this paper really opens up some profound questions. What are one or two of those that you think we should all be pondering after this episode?
I think we need to seriously consider, will execution sandboxes become obsolete for AI training, relegated only to the final integration test before deployment? And perhaps even more critically, if an AI generates a patch and another AI uses a semi-formal reasoning certificate to approve it, who is ultimately responsible when that 7% margin of error results in a production outage or, worse, a security breach? It's a question of accountability in an increasingly AI-driven world.
That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend or drop us a review.
Keep reading the fine print.